Good afternoon, everybody. So Salvador asked me to chair this session. I think we can maybe wait one more minute for people to reconnect. I just want to share, let's see the agenda. Here. Okay, so we have 3 talks. So everybody can hear me?
Yes, very clear.
Oh, thank you. Right, so we have 3 talks this afternoon. One is by Alfredo Castañeda on optimization of Higgs processes. There's another one by Alexander Baur on flavor symmetry from string theory. And then a long one by Lorenzo on hyperspectives from the theory side. So these 2 are 17 minutes plus 3 for discussion. And this one will be 40 minutes long. So I'll give like a 5-minute warning before the end to the speakers, just to try to stay on time. Okay. So I'll stop my share now. All right, so we have 30 people connected, 29. Fredo, I think you could maybe start sharing your presentation.
Yes. All right. So it is fine like that, or I do full screen?
I think it's better like this. It could be stop or hang if you do full screen.
Okay. Okay, thank you. So I will start. So thank you for the opportunity to talk about this. So this talk is about optimization in the search for rare Higgs processes during the high luminosity LHC using artificial intelligence algorithms. Well, the motivation is clear. So far we have been covering a lot of processes in the standard model with the data collected by the LHC. In both experiments, Atlas, CMS experiments, but there is still a lot of room for studying particular processes which are difficult to analyze with the current data and even with the data in the coming years. What we will have for the LHC 14TB collisions and the future accelerators, the FCC, which aims to go to 100 TB. This will allow scientists to measure what we call kind of rare processes both in the standard model and hopefully beyond the standard model. So as I said, with the data collected so far, we have not been able to measure some processes which are important in the standard model. For example, the double Higgs production, and some of the rare Higgs decays and Higgs in association with other particles. So basically, to access this region, which are in the green square, so we need 2 things. We need, of course, more luminosity. Let's say perhaps at least 10 times more than what we have. But the other things that we also have, we also need better methods to separate the signal and background. A combination of these two things may allow us to have some measurements. So the high luminosity plan for the LHC is clear. So we are now about to start run 3, but the most data that we are expecting is from the high luminosity LHC. That will start around 2025, 2026, and will run until 2035, which will expect a total integrated luminosity of 3000 inverse femtobarn. So far, what we have been doing is, we are commonly what we are doing in high energy physics is for certain kind of searches or analysis, what we do is to start with some basic physics assumptions. Usually what we are doing is that from physics, we know that interesting or events or signal events are located in the high energy or high momentum region. So that's why we cut on these variables to reduce the non-interesting events or backgrounds, and we keep the signal events. However, it was shown that this approach it's not optimal when you have several particles in the final state. So you have correlation between distributions in the signal and the background. So this became not optimal, and most likely you will lose or your signal efficiency. So the alternative method will be the use of what is called the artificial intelligence, and a subset of this is what is called the artificial neural networks, and also boosted decision trees. These are just two examples of this alternative approach to analyze the data. I will talk a bit about this in the next slides. But the benefits from this is that if you apply, well, the benefits from the previous approach or the traditional one is that you have your analysis based on physics assumptions. That is easy the interpretation that this is systematics. However, as I said, there is no optimized separation of signal and background. For the alternative ones, you have a better methods to separate signal and background. You are not necessarily relying on physics, basic physics principles, because you use all the data in all the variables that you need to classify the data. The difficult part is that there is it's quite difficult to assign a systematic uncertainty out of these methods. Okay, talking a bit about artificial neural networks. So the design is not that complicated. They are basically composed of layers of artificial neurons. Each of one is interconnected by a wave factor to the other layers, and there is an output layer. Usually the first data, well, the first layer is the input data, which is usually a collection of variables in different formats. In terms of high energy physics, can be the momentum of a particle, the energy, the angular separation between two particles, the invariant mass distribution, and so on. So the thing about this is they go through a learning process. For example, a learning step is completed once you introduce or you feed the neural network. It goes through all the processes, weights, and interconnection between neural networks, artificial neurons. And in the output, you get a classification of the data, either if it is a signal or background. If the output of the artificial neural network is wrong, so you go back, so the weights are updated based on an error minimization process, and the sequence is repeated. It's learning to let's say, for these objects to learn, you need to use something that you know that is signal and background. So these objects are usually trained using Monte Carlo simulation for signal and background. So the point is that in every iteration, the error should decrease once you achieve a minimum value, so you can declare that the network has been trained. There are another kind of artificial neural network, which is called convolutional neural networks. These are designed to process data as images. In the field of high energy physics, is extensively used to identify jets. So jets is a collection of particles that deposit energy in the calorimeters. Those deposition can be interpreted as images, and based on the pattern of these images, you can build a model that can identify the origin of the jet and even the flavor of it as well. So this has been extensively used for several years in high energy physics. The other approach is to use boosted decision trees. These are kind of also supervised learning. These objects also learn from the data. In this case, each of the nodes representing a category in the data. So you can split it until you find that all the data belong to some class. Again, in case of high energy physics, it will be signal or background. So the output of this boosted decision trees is a classifier. Usually it goes between -1 and 1, as you can see in the graph below. To be able to work with these objects, you need, of course, computational resources. Usually the people at CERN have developed common tools that combine the CERN tools, characteristic of each experiments, and they combine the power of GPU cards to accelerate the processes. As I said, the training data is obtained from Monte Carlo simulated samples, in which you know what is signal and what is background. Once you have these Monte Carlo simulated samples, you usually do a basic event selection. So you need to obtain the variables to input for the neural network. Once you do that, you train the neural network with the common tools. Some of those are open source. One of the most common models to train is TensorFlow and Keras. And to be able to accelerate the process, usually you use GPU cards to get results faster, because this involves a lot of matrix operations and so on. And finally, you get the results, and then you have the interpretation of results in terms of your physics. Just a bit about examples about how to use this technology for some analysis. These are mainly focusing on what people can call like rare processes. To describe what is a rare processes, they have to at least to share two of these characteristics. They have a low cross-section and branching ratio. They usually have a large background contamination contribution, and they can have also large object multiplicity. If all these three characteristics are there, so you may be able to use some of these alternative methods to obtain some benefit out of it. So one of the processes, as I said before, is the Higgs processes. In this case, the Higgs decay to mu plus mu minus. This has not been yet measured, but this can provide the first evidence of the Higgs couplings to fermions, which are outside the third generation. The difficult about this is that they has a low branching ratio, and they have a very big contribution, mainly from Drell-Yan. There are different mechanisms for the production of this, for the decay of these Higgs, BBF, BH, and TTH. The dominant one is the gluon fusion, as you can see in this table. Here you can see the simulated signal for the Higgs to mu. The way to use this is that what you do is you build a boosted decision tree using several kinematical variables. So one of those related to the properties of the dimuon system, the PT, the eta, the delta eta, the delta phi between the muons. If you have jets in the vents, you can also introduce some of these variables. You put all these variables in the boosted decision tree, and then you have the output of the BDT, which in this case, it goes from 0 to 1. Here you have all the components of the simulated Monte Carlo, and also the data as well, and the signal. So basically, what you can see is that by using this BDT classifier, you can get, well, the most of it, you can get a 0.48 signal over background discriminator, which is quite good. But this has to be improved if you want to actually measure this process. Other ideas is to use not only BDTs, but also deep neural networks with several layers to also improve the performance of this classifier. Another process interesting is the Higgs to BB. This has the largest branching ratio, which is about 58% of all the Higgs decay modes. So the problem with this is that it has a large and irreducible background process, which is the QCD. the advantage of measure with high statistic or with high purity this process is that it allows us to get information about the high PT Higgs production, which is difficult to measure with the other clean decay modes, as the Higgs gamma gamma, Higgs 2,4 lepton. But the problem, as I said before, as you can see in this plot, is that you have enormous background contribution from QCD processes. So what you do here is that you use what I described before, this CNN
5 minutes, Alfredo.
convolutional neural networks. Yeah, in this case, what you do is, again, you focus on the jets, on the B jets. As you can see, these are pictures of B jets, how they are detected in the calorimeters. So you can see the difference. The first row is the background, and the second row is the signal. They have different patterns. When you introduce this to a convolutional neural network, you get a classifier that can distinguish between signal and background. Applying this to the results, you can get this. So you can see the red solid line is what you will get if you apply this neural network, and the dashed line is if you don't apply it, and you can see a huge improvement of that. By saying by word, you can say that you can find evidence of 3 sigma with the 2002 with the data that we have right now, and possible observation with the high luminosity LAC. With the neural network, without that, you will require, of course, more data. You can see here the integrated luminosity to measure properly this decay mode. So the dye-Higgs search is another one which is important. Here you have several decay modes. It's important because you measure the trilinear self-coupling of the Higgs boson. This provides important information from the standard models. Here you have the different, each of the Higgs can indicate to different particles. Of course, the BB is the one that has the highest branching ratio. Here again, for specific decay modes for the BB and 2 vector bosons, you can use, again, neural networks in which you combine you feed these neural networks information about the leptons and the jets, and you can build a classifier, in this case from 0 to 1, with different invariant mass ranges for the jets, in which you separate signal and background, and you can see the performance. Similar for the BB to tau tau, in which you can use boosted decision tree to reject the TT-bar background. So the last one is the Higgs associated with the top quark pairs, the TTH. In this case, what this characterizes is that you have large object multiplicity in the final states. You can have up to 8 objects in the final state. And so you can use, again, neural networks to separate signal and background. Some of the distributions that you can see seem similar, but when you input this to a neural network, you have the power to discriminate between signal and background. Here in this plot, you can see the background efficiency, signal efficiency versus background efficiency. As you can see, these are just different architectures of neural networks, but all of them give some improvement. So, okay, so the conclusion is that the observation of rate processes related to the Higgs and the Higgs rare decays depends on the data that we are able to accumulate in the following years and the development of the new analysis techniques. It has been shown that the integration of machine learning techniques for several final stages can increase the signal purity and also the possibility for observation of these states in the following years. And there is a need for the scientific community to spend computational resources and manpower to be able to collaborate in these developments. Thank you.
Thank you very much, Alfredo. It was very nice. We have we're even early, so we have 4 minutes in case there are questions.
Yeah.
From outside.
Yes.
I have a question. If no one has a question, I'm Cecilia.
Yeah, go ahead, Cecilia.
Okay, thank you. So very nice talk, Alfredo. Thank you.
Thank you, Cecilia.
What I want to ask you is if your group is involved with some of these studies for the channels that you mentioned or some others.
Well, I'm starting to collaborating with the double Higgs measurements in particular. So we have a strong group of analysis in Sonora, but we also have a strong group of data scientists. So we are trying to combine both expertises and also the computational resources that we have in University of Sonora to make some important contribution in these areas.
Okay, thank you.
Yeah.
More questions? Well, I can ask one. Nobody else.
Mm-hmm.
I mean, since you're very much into this machine learning and multivariate techniques, I mean, there were so many algorithms that have been developed, let's say since run 1, run 2, to optimize the searches. So it's quite difficult sometimes to choose one, right? To apply to your search.
Yes. Yeah, it's quite difficult, but it also depends on your kind of topology of your analysis. And here I'm just talking about the offline analysis, because all these methods have been also implemented in the online for particle identification, for triggering. This is not part of this talk, but here are only related to offline analysis. And as you said, it's difficult because it depends on your signal. You have large multiplicity, several variables. Most likely you can use a neural network. If you have low multiplicity, but I don't know, the process has a large branching ratio, you can use another one. It depends. Yeah, it's not fixed. I mean, you need to perhaps try different approach and see which one works better.
Thank you. No more questions? I think in that case, we can go to the next talk. So, Alexander, are you connected?
Yes, I'm connected.
Great. Yeah, I can see your slides now. Yeah, go ahead and I'll give you 5 minutes at the end warning, okay?
All right, perfect. So let me start first of all by thanking the organizers to give me the opportunity to talk to you today. I'm Alex. I'm a new PhD student from Dr. Ramos at the Physics Institute, and I'm doing my PhD half in Mexico and half in Munich. So as the second last talk of this conference, I will try my very best in keeping this next 20 minutes interesting, which is why I decided to start with a fairly strong sentence. I think that every pattern we observe in nature deserves to be looked at from a symmetry perspective. And we do this by either starting with something we know works, like the standard model, and adding a symmetry to it. Now, this approach will be called the bottom-up approach. So the other thing we can do is we start with a, let's say, higher theory from which we are, of course, not yet sure whether it is of any use to describe nature or not. But what we can do is take this theory of higher energies and see whether it gives us a symmetry for exactly the patterns that we observe in nature. And this is what I would call a top-down approach. And this, of course, also answers the question of the origin of the symmetry. Now, but what pattern am I talking about? I am talking about a specific flavor structure that we observe in nature. So we do observe 3 generations of standard model particles, and we observe the mass patterns of quarks, of leptons, and even of neutrinos. And of course, we observe their mass mixings. So I'm referring to CKM and PMNS matrix. And the simple symmetry-driven explanation would be to just add another symmetry, G flavor, that is orthogonal to the gauge symmetry, or over here, orthogonal to the gauge symmetry. And yes, so what are my goals for this talk? First goal is to try to convince you that flavor symmetries arise naturally from extra dimensions. And the second goal would be to show that orbifold compactifications give rise to eclectic flavor symmetries. Now, before that, I want to give you a one-slide overview about what bottom-up people are doing currently and what they're considering as flavor symmetries. So in bottom up, there's this traditional way, which has been around for quite some years now. It works roughly like this. So you impose some discrete flavor symmetry, and you add some extra particles called flavons, which will break the flavor symmetry. Now your standard model particles transform with a representation rho under this flavor symmetry, and the Yukawa couplings are constants. Now the most tricky part about this way is the next part, namely you have to give VEFs to all the additional particles you added, and you have to align those VEFs very cleverly in order to be able to describe what nature gives us. And yes, so my favorite review about this approach would be by Petkov, and I also want to highlight this one example here. Because it has been done here in Mexico. And so these guys proposed an A4 symmetry for quarks, leptons, and neutrinos, and managed their model to be in actually spectacular agreement with the observed data. So this was one way. And there's another way, which for me, it looks very promising. I would call it the modular way. And this works like this. So you impose a modular flavor symmetry, which also means you add some sort of modulus to your theory, or even multiple moduli for that reason. Now your standard model particles, they transform with an orthomorphy factor under the flavor symmetry. So they still transform with the representation of the flavor symmetry, but there's this additional orthomorphy factor, which also depends on the modulus. And most importantly, the Yukawa couplings are now modular forms. They're not anymore constant, they're modular forms, which means they're somehow functions of this modulus T. And what you now do is you give a vacuum expectation value to the modulus, so only to the modulus, since you didn't add any additional other particles. And yes, so the seminal paper on this would be by Ferrulio, and I want to highlight one example of again an A4 symmetry, but this time a modular A4 symmetry. And I wanted to highlight this paper because they did the quark, the electron, and the neutrino sector with one A4 model, and this has never been done before. So this way is very new. It's only 3 years old, and it looks promising for me. Now, after this one slide of bottom up, let me now come to top down and what the title of this talk actually promises you, namely flavor symmetries from string theory. And well, in case you were worried that you might need to know a lot about string theory to follow this talk, let me lift this concern by telling you what you need to know about string theory, at least for this talk. And this is only one thing, actually, namely string theory comes with extra dimensions. And well, usually it's 6 of them. So what do we do about an extra dimension? Well, we roll it up. So let's take a look at one extra dimension. We roll it up to a circle such that it is compact, and we make the circle very small. This number is just to give you a rough overview about how small I'm talking about. And then we have one compact dimension. So you can add another circle or another dimension, and this will yield you a torus. Now, of course, I said usually it's 6 extra dimensions, so we can take 3 of those tori and make them orthogonally to each other, but this is a bit complicated. So let's focus on a 2-dimensional subspace, a torus. Now, the thing with the torus is it leads us into problems with supersymmetry, which is why we think we might just take this torus and divide it by 3, or mod out a Z3 in a abelian group, which will yield us this funny object over here. Now, I don't know whether you like Italian cuisine, but if I paint this in yellow, this really looks like a 3-sided raviolo, doesn't it? And since I find ravioli quite tasty, let us try to extract some flavor out of this raviolo. And well, we therefore take a mathematical look at it. And we cut it open on those 2 sides here. And we will get those 2 triangles over here. So we'll see that our raviolo has 3 singularities, x, y, and z. And what we of course also want to know is how do our strings live on this raviolo? So first of all, there are those winded strings that wind around the raviolo like an 8, but they're quite boring for today. We're interested in the twisted strings. They are roughly localized at the singularity. So their center of mass is at the singularity. And those are the strings that are interesting for today because they are massless, and massless in the sense of string scale massless. All right, this means we have like 3 identical copies of the same string on these 3 singularities, which might already hint towards a flavor symmetry. But now, how will we generate a flavor symmetry out of this object? And of course, this has been done in the past. And for this, I would call it traditional approach, at least for the first part, you don't really have to be a string theorist. You look at this object, you see 3 points, you can change them in any possible way, which will give you an S3 geometrical symmetry. Now, what you also do is you take a look at the strings, see how they interact with each other, and then you get this other string selection rules. You multiply them together, and you will get a flavor symmetry for this object over here. The symmetry group of this flavor symmetry will be delta 54. So delta 54 is the name. All right, I will call this a traditional flavor symmetry. So yeah, traditional flavor symmetries have been considered here, and there's also been pheno done with delta 54 as a flavor symmetry. Now, what we did in the last 2 years is take a more abstract look at this flavor symmetries, or take a more abstract approach to actually the same problem, namely to get the flavor symmetry out of the object. And so this new approach, we do it like this. We take our raviolo space-time and we describe it by a mathematical object. Well, it's going to be called the space group. And then we derive the symmetries of this mathematical object. And the symmetries, from these, we will then get the flavor symmetry. Now, I figured that the details will be quite boring for this conference, which is why I will go straight ahead to the results of this new approach. So for our orbifold here, for this raviolo, we also find this flavor symmetry, this traditional flavor symmetry, delta 54. And now you can imagine, as a very young student, I was really relieved that my new approach reproduces the same result that numerous of professors have been predicted before. However, the new approach additionally yields another symmetry group, namely a double cover of A4. And how can it be that we find this additional symmetry group? And this is because we totally forgot about something, namely our orbifold is based on a torus. And if you want to parameterize a torus, we do this by 2 circles, the omega 2 and omega 1. You can divide those 2 circles and we get a complex number out of it. This will be called the modulus. Now, if we take the same torus, the exactly same torus, and parameterize it differently, we will get a different modulus. Well, luckily, those 2 moduli are connected to each other by those 4 integer numbers, A, B, C, and D. So those integer numbers, A, B, C, and D, they generate the so-called modular symmetry, which is, so roughly said, it's the symmetry of how you parameterize your torus. Okay, so now for orbifolds, I failed to draw the parameterization because it is really hard to imagine, but you'll have to believe me that there are 12 different ways to parameterize the same orbifold, and this will give rise you to a double cover of an A4 modular symmetry. Okay, now you remember right in the beginning when we divided the torus by 3. Of course, we could have also done this and divide by 2, or divide for the fact by any other number. And let me tell you that there are 16 different ways to divide a torus. So those are the 2 ways that we have looked at by now, and there are of course more ways. So we have looked at them with the new approach. The traditional approach, of course, has looked at all the 16 ways. So if we take this, if you divide by 2, if you take this other T2 over Z2 orbifolds, we will get another raviolo. This time it has 4 sides, so it really looks like a real raviolo. Or we might even get a tetrahedron, or any shape that is somewhere between this raviolo and this tetrahedron. So the shape is not fixed in this Z2 orbifold. Again, with the approach, we yield a traditional flavor symmetry, which will be this one over here, and we will yield a modular symmetry. This now has two moduli, the one that you just know from here, and there's another modulus which describes the shape of those two. All right. And there's a Z2 that interchanges the two moduli. Okay, so now I hope I managed to achieve my first goal and convince you that flavor symmetries can arise from compactification of extra dimensions, and which is why we now can take a closer look at these flavor symmetries. So we always got the traditional and the modular symmetry. As a matter of fact, we can also take a look at the representations. So we will do know which representations our strings form under this traditional flavor symmetry. And especially in this case, we'll see that our strings will form a triplet under the delta 54 and a 2+1plet, which is also fine for a 3-generation.
5 minutes, Alex.
5 minutes? Okay, thanks. Under the modular symmetry. So this looks very promising phenomenologically speaking. Good. So we always observe this traditional and this modular symmetry. So we have the traditional and the modular symmetry. And what we observe is that those two are not orthogonal onto each other. So there has to be some sort of semi-direct product here, but our research field is still in the process of finding the right names for the right objects. So just to be on the safe side, let me put a union between those two groups here. But keep in mind, they are not orthogonal to each other. Nevertheless, we observe that the combination of both the traditional and the modular symmetry is there. And we observe that the combination of both forms the eclectic flavor group. Now, you remember the non-orthogonality of those two groups. And well, this actually puts tight constraints on the two symmetry groups. First of all, this means that the traditional flavor group has to be a normal subgroup of the eclectic group. And we will also see that the modular group actually can only consist of outer automorphisms of this traditional flavor group. Now, as you can imagine, there is only a very limited amount of possible combinations of those traditional and modular flavor symmetries, which is, of course, good news from a bottom-up perspective, since you don't have to try out that many symmetry groups. Okay, so what we can do next is we take our modular symmetry and we give a VEF to the modulus, which means we break the modular symmetry by the VEF of the modulus, and this traditional flavor symmetry will then be later broken by the VEF of the flagons. So what we can do is we take a look at each possible VEF that we can give to this modulus, which will give you somehow the moduli space, and see which remnant flavor symmetry we will get. And for the Z3 orbifold, we can now draw this nice picture here. So this is the real part and the imaginary part of actually the VEF of the modulus. And if we are on this reddish area, we will get a remnant flavor symmetry of delta 54. However, if we are on some of these special points or lines here, we'll get a higher order flavor symmetry of those higher order groups. Yes, those groups are referred to the small groups library of GUP, if you're interested in them. And we also had this other orbifold or raviolo, the Z2 orbifold. We can draw the same picture here with the real and the imaginary part of tau. The fundamental domain is now a bit different because we have a different modular symmetry. And yeah, we'll get those flavor groups here. Now, you remember there were two moduli for the Z2 orbifold, and now this is one of the modulus, and we say here that the modulus is just takes some unspecial value. Well, if this modulus U actually takes e to the pi I third, which means that the shape of this orbifold is the tetrahedron and not any other funny shape, we'll get different remnant flavor groups, and they are all written down here. I won't go into detail of them. Okay. So I'm a bit fast. Anyway, concluding, the main two takeaway messages from my talk are hopefully that flavor symmetries naturally arise from compactifications of extra dimensions. And the second main takeaway message will hopefully be orbifold compactifications give rise to eclectic flavor symmetries. So these eclectic flavor symmetries consist of traditional and modular symmetries. Now, you probably remember that the bottom-up considered either traditionally or the modular symmetry, so they separately considered them, while the top-down actually predicts that both of them should be there at the same time, and they're actually not orthogonal to each other, so we always have to consider both of them. And of course, I wonder how all these setup would influence the neutrino physics and the dark matter physics mentioned, among others, by Dr. Garces, Newton, and Lewis' talks today. Well, and finally, I hope that next time you're eating ravioli, you are thinking about flavor symmetries. So, thank you.
Thank you, Alexander. That was very nice slides with the diagrams and everything, very, very clear. Questions from people, and I don't know if there's any in the YouTube.
No questions on YouTube.
Okay. And anybody here in the Zoom?
Colby?
Yes, I would like to know, could you apply this scheme to any number of generations?
Yes, so if you see here, we got triplets. So this will probably give us 3 generations. And so this orbifold here has a 4-plet, so we'll, yeah, I mean, this orbifold will probably give a 4-generation model, which is, I guess, a matter of taste, whether you like it or not. Does this answer your question?
Yes. I mean, you know, there is a qualitative difference between 2 and more generations because CP violation comes in. Is this somehow taken into account by this scheme?
Of course, you probably know my work. There's also CP involved here. So this CP sits in the modular symmetry actually, and yes, how could we say? So there, if we let me go right to the beginning. You remember those winded strings? If we only had 2 winded strings and not 3 of them, then a CP transformation would be possible. This was a paper, I don't know, 3 years ago by Hans-Peter Nilles, Patrick, and Andy Trautner. So they saw that if you only have 2 of those strings, the CP transformation is in general possible. So the CP transformation in the sense that the triplet of X, Y, and Z is mapped to its complex conjugate. However, if those 3 winded strings are present in your theory, then the CP is violated. So there's no transformation that maps X, Y, and Z onto their complex conjugates right away.
Okay, thank you.
One more very short question, if there is.
Yes, there's one, Miguel Ángel Hernández.
Go ahead.
Thank you. Hi, Alex. Thank you for your very nice talk. I have a question regarding the origin of the modulus that you need to break the modular symmetry. As in string theory, it's kind of weird to add new particles. Where from this modulus came from?
Where this modulus comes from? So one modulus comes from the shape of the orbifold. So for the Z2 orbifold, you probably remember that we had these 2 possibilities of either the pillow or the tetrahedron or anything in between those 2. So this is the complex structure modulus, we call it, or the shape modulus, which somehow describes, first of all, the length of those 2 and the angle between those 2. The other modulus contains the the metric, so the absolute value of the metric, or better said, it contains the compactification radius as one part, and the other part would be the B field, the background field, the Kalbromont background field. So those are the two moduli.
Yes, thank you, Alex.
Okay, so thank you very much again, Alex. We need to move on to the next talk. Lorenzo.
Yes.
Great. So you can start sharing.
Okay.
Thank you. And again, I'll just give you like a 10-minute warning at the end.
Okay. Okay, so here is the title of my talk. I'm going to talk about perspectives from the theory side after the LAC. The content of my talk is the following. First, I will say a few words about our journey into the energy frontier. Then I will discuss the lessons from the LAC at the present on searches for Higgs, beyond the standard model, and also quantum field theory. Then I will discuss a bit about the future of Hebb theory and the phenomenology. And then I'll jump to say some very personal remarks on how the field is moving, focusing on model building and also some of the theory aspects, to end with the conclusions. So we are now quite sure that the LHC has been one of the most successful experiments ever, maybe not only in physics, but in whole human history. Now we have all the beautiful results from the LHC that were planned a long time ago, and but the history has not been as smooth as we see now. There was a time when there was this accident at the CERN, at the LHC, that delayed the plans for some time, but after that, the LHC fulfilled the goals that it was planned to do. So now we are in a kind of a pause and waiting for the next phase of LHC and what is called the RON 3, and with the high luminosity phase. So in a sense, I see that we are like in climbing a mountain and then taking some breaks to see what we have achieved and what comes next. Now, coming to the lessons from LHC, the specific lessons I will say are the following. First, the standard model is passing all the tests of the LHC, so the principles in which the standard model is based are very solid, and then we also learn from the LHC that there is a Higgs boson, and is one of the greatest achievements of the accelerator. At the same time, we have the absence of signals of new physics, or physics beyond the standard model, which is quite intriguing. So this means that we have to keep improving the experimental tools and also to think harder. In general, this is a situation in which some people is kind of unhappy. But for me, I find that this is a very interesting time, very challenging and exciting. And so actually, for me, as I said several other times, just finding with the discovery of the Higgs boson has been one of the happiest moments in my career. Regarding the specific aspects of the Higgs boson and electroweak symmetry breaking, we learn from LHC several important facts. we remember that the standard model is renormalizable. It's a gauge theory that includes spontaneous symmetry breaking. Then from that theory model, the Higgs boson couples to the mass. That's the essential property. And it's very simple to look at this just from this Lagrangian that we have the coupling of the two fermions and scalar. The scalar develops a vacuum expectation value. Then bilinear in the fermions is the mass of the fermion, and at the same time we have the interaction of the Higgs with the fermions, and is proportional to that Yukawa coupling, which is expressed in terms of the mass and divided by the vacuum expectation value. So this is the very, very important property of the Higgs, the fact that it couples to the mass. And that is what made so difficult to look for it at the experiments. Given the Lagrangian, we have the couplings of the Higgs boson to fermions, top, bottom, tau, and also to gauge bosons. At tree level, we also have these couplings at one loop with gluons and with photons, mediated by the top quark in the case of the gluons, and also top and W in the case of the photon. So the main outcome from this Lagrangian, from these Feynman rules, is that we can calculate the branching ratio of the Higgs particle. And there in the figure, we have that all the relevant modes that are in the range of that was preferred before the Higgs discovery by the electroweak precision test. And it's very nice that nature has provided us a particle that has so many decay modes that can be studied. Then we can also calculate the cross-section through different mechanisms like gluon fusion, vector fusion, associated production with WC, and associated production with the TT bar. With this, the experiments, or before the theories estimates, gave the signal that can be studied at LHC. And just to remind what was achieved at the first phases of LHC, I include here some comments. First, the Higgs signal that was discovered. First, it was through the 4 lepton channels and the photon pairs. Later on, some extra modes were also detected. And I have there a table with all the results that were obtained at RON 2. At RON 1, sorry. From that, we learned that the Higgs mass was in the range 125, 126 GeV, and this measurement has been made more precise. We also learned from the early runs that the Higgs has to have a spin 0 because of a Young theorem that vector particles cannot couple to other vector particles. So it has to be spin 0. Actually, spin 2 was also a possibility, but later on more measurements excluded that. We also learned that the Higgs is a CP even state because it couples to vector bosons. And initially some deviations were reported for the standard model for the Higgs decay into photons, but these numbers were gone later. So already from the round 1, we learned that the Higgs behave pretty much like the standard model. Later on, it came the results from the second phase of LHC, the round 2. Some of them had been already discussed in great detail in the previous talks. So just mention a few of them. There are new standard model channels that were detected. Actually, in round 1, the decay of Higgs to BB bar was not detected with enough confidence, neither the TTH, which was something that came with round 2. There are also bounds on rare standard model signal, Higgs to mu pair. And overall, there was this whole variety of combination of decays and with the production mechanism. In this plot on the right, I include this because a beautiful display of the existence of the Higgs boson that we can show to undergrads or even high school students, that there is a particle that is responsible for the generation, or part of the mechanism that generates masses in elementary particles. As I said, the lesson, or one of the characteristics of the Higgs is that it couples linearly with the mass. And this has been verified, as is shown in this other figure, that the couplings of the Higgs with different particles lie on a single line. This observation that all the couplings with all fermions lie on a single line, I find this very interesting, and also something to look at in other models, as I will discuss later on. So in this, the Higgs couplings of the Higgs can be described in this kappa formalism, where one parameterizes deviation from the standard model just by simple couplings that go with the standard model couplings. This is an overall factor for the W coupling, another one for the C boson. This is kappa W and kappa C. And similarly for the fermions. Now from round 2, we have these really impressive results on the limits on these kappa factors. We can see from this table that the Atlas and CMS have reported that for tau, bottom, tau, C, W, all the numbers are now very close to 1, which means that the standard model seems to be the interpretation of the Higgs modulo de uncertainties. It's also interesting that the LHC is already providing bounds on the coupling to muons, which are already quite close to what one expects in the standard model. And this is very interesting of how the experiments learn, and are the experimentalists are improving their methods. I remember one of the, 10 years ago, I asked some colleagues about the possibilities to detect the muon, and they told me that it was very difficult, the numbers will be very poor. But look, here the numbers are quite impressive. And sometimes one hears that the Hadron Collider is ideal for discovery, but not for precise measurements. But again, in the case of the Higgs, thanks to this very detailed and sophisticated analysis of signal and background, we are learning even couplings of the second family. Besides this coupling to the muons, now there are also limits on the couplings with the charm and even with the strange. Now we can see from these plots from the LHC round 1 that this correlation of modifications of the coupling of the Higgs with bottom, and also with modification of the coupling with charm. This is because of the way that we search for a bottom, and it's possible that in some of the Higgs decay to charm, and so charm will be included in the signal, and then by comparing the events and the distribution, the LHC collaborations are able to put these constraints. So at the wrong one can see that the couplings for the bottom will be in the range of order 5, -5, and for charms between -20 and 20. And now this has improved considerably when one goes to round 2, we can see here that the limits now have reduced to, instead of order 10, they have gone to order 1. And they will be even better at the expected high luminosity phase of the LHC that will come in the kind of near future. Besides those standard model signals, LHC has also studied signals beyond the standard model. Some of them include the Higgs decay into invisible modes that could be like dark matter, for instance. And there are limits still order 1 on the branching ratios, 0.5, 0.6. We also have limits on the decay of Higgs that violate the lepton number, like Higgs to tau mu. Exotic decays, Higgs going to gravitinos and photons, but no signal has been detected. Again, some years ago, there was a claim that the Higgs to tau mu was observed, but the rate was just too large to be taken seriously from the theory point of view. It was very difficult to reproduce that result. So later on, it disappeared from the data, which is consistent with the models which predict actually smaller rates for branching ratio of Higgs to tau mu. So we are starting to talk about physics beyond the standard model. And this is what I think. So the standard model is great, but there are open issues, as it has been mentioned before. We have the neutrino masses that have already been detected, dark matter, dark energy, the baryon asymmetry of the universe, the more aesthetic questions like why the standard model parameters, why 3 families. And we also have the problem that the standard model doesn't include the gravity. Is there a quantum theory of gravity that should be combined with the standard model? And to answer some of these questions, many extensions of the standard model have been proposed in the past 20, 30 years. There are models that add extra Higgs doublets, more gauge groups, more fermions, even more dimensions. We have large, extra large dimensions, universal dimensions, quantum dimensions, etc. And then we have the more elaborated extensions that have like more principles, I would say, like supersymmetry, grand unified theories, and even string theory. So in this, we have had a great time building one model after the other. And maybe there are more models than theories, because theories can contribute with more than one model. But that's the party, that was the party. Now we have the situation at the LHC is that no signal, conclusive signal of physics beyond the standard model has been detected. This means that the LHC should be closed and the theories be fired or punished? Of course not. Even not finding signals here teaching us. And here I just display what this summary from the LHC, from the CMS, and on all type of extensions and models that have been extended. So for instance, the extra gauge bosons, like a neutral gauge boson, now the limits are on the order of 4 TeV. For large extra dimensions, the limits are also around, now getting close to 10 TeV. And these large extra dimensional models were motivated with the idea that we have a TeV scale. So it's clearly a bit difficult to motivate them as initially they were proposed. if we look at the compositeness, the idea that the quarks, leptons, gauge bosons are composite, we can see that also the limits are really, really impressive. They are getting close to 18, 19 TeV for electrons, for instance. So this is the beyond the standard model situation. But is this really teaching us something? First, we need to, I think, in the 80s and 90s, there were some arguments for expecting order 1 TeV scale for new physics. Those arguments have to be re-examined because the new physics is getting beyond that scale. But there are, of course, the open problems of the standard model that remain. So in one of these motivation was to think that nature has to be natural and that the standard model is not, so that we need something else to make it natural. But that, at least within the context of the model that has been proposed, seems that it's not working. So we have to think harder on those issues. So is there new physics? Is consistent with quantum mechanics and relativity? How is UCI realized in nature? So I have this image of like this game of ladders and snakes that you expect to climb, and if you lose, then you go to the initial stage. So the idea was that you have the standard model, and then at the TeV you will have an extension of the model. Then at much higher scales you will have a grand unification where all the three interactions, strong and electroweak, will unify. And after that, at a higher scale, at the Planck scale, it will be the domain of string theory or some other theory of quantum gravity. And the experiment has told us that game is not as straight as it seems in the 80s. So we have to think again carefully what we were doing. But there is no panic situation. We have to also look with serenity at this situation. First, the first caveat that one has to take into consideration is that the LHC is not done yet. So we have to wait for the next high luminosity phase to see if the LHC will find new physics or not. One also should search for these signals at higher luminosity or at higher energy. Also consider the intensity and the cosmic frontiers. And eventually, maybe we will have to discuss arguments for building, to motivate the building of next colliders, a linear collider or a very large hadron collider. And of course, at the very end, we can ask help from Mexican models with this image that I think Mexicans will understand. So let me now jump to some comments on the theory perspectives on three aspects: on phenomenology, on model building, and then theory and the formalism. So first, in the phenomenology, what we can say is, okay, so far there are no signals of the beyond the standard model, but we must keep looking. But we also have to consider very carefully what we have and what we claim that we have. And if we compare the model that have been built, they include nice ideas, technicolor, extra dimension, supersymmetry, but they are not really a final model, a complete model that will substitute the standard model. So those ideas, in order to develop, to solidify, and to pass, need to have a experimental input. We need the help from the experiments, which is what keeps healthy our field. Otherwise, we will speculate as much as we want. And another aspect is that many of those models, rather than focusing on the principles and the nice ideas that are behind them, they can also be seen as a generator of signatures. So, for instance, when in the 80s it was minimal supergravity being discussed, and the presence of a lighter supersymmetric particle, that motivate signals with missing energy and, of course, dark matter. Then, when in the 90s, these models of gauge mediation of supersymmetry breaking were constructed, it was realized that those models include a very light gravitino, and then the superpartners that appear in the minimal supersymmetric standard model will decay into gravitinos and also photons. So there will be signals of missing energy and photons. Now, if we go beyond those scenarios and we consider, for instance, a gravitino at the electroweak scale, which is the lightest supersymmetric particle, then dark matter will be the gravitino. And in this case, a completely new class of signal will appear, namely that the next to lightest supersymmetric particle will be long-lived. And then, for instance, a stop or a stau will not decay within the detectors. And so this is a very different signature. And we need to keep looking at those. Then we have this very novel model, the 2 Higgs doublet model. And in this case, we can see that this model gives a rich spectrum of Higgs particles, a heavier neutral Higgs, and also a charged Higgs. And using that model, we learn how to search for those particles. So we need to keep take a closer look at the patterns and events and look for surprise, which may be around the corner. Just a comment, in Mexico, we now have several groups that work on 2 Higgs doublet model. And I will always say that this very novel model was brought to Mexico by Miguel Ángel Pérez from Sinvestab. So let me discuss a very basic aspects of the 2 Higgs doublet model, which I will discuss later on. First, we have in the Yukawa sector, we have that the fermions, the quarks and leptons can couple with the 2 Higgs particles now, and we can have very several types of models. Some of them include flavor change neutral currents, others do not. And so we have in the model 2 Higgs doublet models, 2 Higgs doublets. If we have in the standard model 1 Higgs doublet that includes 4 degrees of freedom, as we know, 2 of them become the longitudinal modes of the charge W, and 1 of them becomes the longitudinal mode of the Z boson. So out of those 4 degrees of freedom, we are left with only 1, which is the physical Higgs particle. Now, if we have 2 Higgs doublet models, 2 Higgs doublets, then we have 8 degrees of freedom. Again, 3 of them become the longitudinal modes of the gauge bosons, and we have 5 physical particles in the spectrum, which are the light Higgs, which is interpreted as the standard model 1 that has been observed. Then we have 2 extra neutral heavy Higgses and also a charged state. So the parameters of the model are the 2 vacuum expectation values of each Higgs doublet, which are traded by the combination of the square of those values, and to give the 246 GeV value of the vacuum expectation value in the standard model. And then we also have tangent beta, that is the ratio of the two vacuum expectation values. Also, we have the masses of the heavy Higgses, and alpha, which is the angle that appears in the diagonalization of the neutral Higgses, the h and little h. Actually, tangent beta is the angle that diagonalizes the mass matrix in the charge and the CP-odd states. So we have here all the type 1, type 2, type X, Y, type 3, where depending on how the Higgs is coupled to each of the fermions, we have that defines a model. For instance, in the 2 Higgs doublet model of type 1, we have that 1 Higgs doublet gives masses to all the fermions. In the type 2, we have that 1 doublet gives masses to up quarks and another one to down quarks and charged leptons. But remember that we said that one of the essential features of the Higgs is that it couples to the mass, and it gives a linear relation as when we plot the Higgs couplings as function of the particle mass. However, if there are more than one Higgs doublet, the single line will be replaced by a more complex arrangement of lines, depending on how the model is constructed. For instance, in the 2 Higgs doublet model of type 1, where all the fermion masses come from a single doublet, then all the Yukawa couplings will also lie on a single line. But this line will not coincide with the standard model 1. So there will be an opening angle between the standard model and the line associated with this model. On the other hand, for the 2 Higgs doublet model of type 2, we have that 1 doublet gives masses to up quarks and another one to d and leptons. And in this case, we will have two lines. So we'll need to consider two angles that will make these lines with the standard model. So I have been saying this for some years, but finally I found how to calculate, how to go more quantitative about these Yukawa lines.
Lorenzo, 10 minutes.
Sorry?
10 minutes left.
Again, sorry?
10 minutes left.
Okay, thank you. So very recently with Marco Arroyo, and we calculated the angle in terms of the fermion masses and the Yukawa coupling. We had that expression. And in this figure, we can see very clearly that depending on the parameters of the 2 Higgs doublet model of type 1, we will have different lines. And, but of course, we need to have the line that associated with this model should be in agreement within the errors of that have been measured for all the couplings. So we have done a very detailed analysis of this, and in these other figures, this is for type 1, and this other one is for the type 2. And we have identified the regions of parameters that satisfy all the constraints from Higgs observables, and also these fixed lines for the values of the angles. So we can see that this is of the order of 10 to the minus 2, 10 to the minus 3. And that are the values of this angle that satisfy all the constraints. While in the 2 Higgs doublet model of type 2, we have larger values. So we need to have a better measurements of the Yukawa couplings in order to find a comparison. So this is, I can say, it's a new test of the standard model. Now, talking to surprise, so very briefly, I will mention, I just learned this last week, that the CMS has reported an excess of events in TT production, CT-bar production, that is, the data is just 1.9 sigma, so it's not a very significant statistic, but this is just, I want just to put this as an example of the surprise that we cannot just forget about them. So the experiments have to look very carefully at these events. So in the figure we have the gray line is the region that should be expected to be excluded in the plane tangent beta MA. And the actual data excludes a different region. So there is a tension around 400 GB, which this is very interesting news, and we have to wait for the next phases of LHC in order to see whether this is just a fluctuation or there is something there. So we have also examples of signals of long-lived stops, but I'm gonna skip this. Then we have lessons for model building. We have the history of unification, how physics has evolved to describe the interactions from different sectors and how they have been unified in particles at the level of the electroweak theory and QCD. And this history is very interesting. Some people think that this is like a bright idea that somebody comes with and then writes the paper and then waits for the Nobel Prize. But that's far from reality. What really happens is that people struggles, builds one model after the other. If we don't have data, we are not sure which model is the correct one. So to illustrate this, how particle physics is done, I include here the paper of Steve Weinberg, a model of leptons, the one that was based on the Glashow paper on the electroweak unification, and which included spontaneous symmetry breaking to make the standard model, or waiting for the contribution of Glashow, Viliopoulos, Mayani to add quarks to the model. So if the vision that particle physics is done like a genius, bright ideas, and then wait, there is another paper by also Weinberg, 77, in which instead of SU2 cross U1, he proposed SU3 cross U1. So we may ask which Weinberg is the good one, the genius that wrote this paper, a model of leptons, or the professional particle physicist that was writing one model after the next, because he didn't have enough data to conclude which one is correct. So this is illustrated in this expression by Freeman Dyson. Great scientists start new fields of science by making leaps in the dark. Nature decides which of the leap is right and which is wrong. So Weinberg did what he could. He wrote 2 papers, and nature chose the first one. And it's very interesting just also to look at the citations. We can see how Weinberg paper, like 3-4 years, have 0 citations. And this is the correct paper. And then the not correct paper had a lot of citations at the very beginning, and then later on it became less and less cited. So this is good news if our paper doesn't get citations at the very beginning and it has a good idea, so we need to keep trying. And of course, there are other signals of new physics that should motivate us to keep working on models. So then we have some comments on theory, and there are like 2 approaches to work on theory. For me, the one that I like is when the theory confronts experiments. That's the goal of physics, to describe the universe. Other people prefer other approaches, so that's fine, but we like to work on along the lines that eventually will be confronted with experiments. So we should first remember that the QCD has been proved at LHC. the LHC have tested, the work of LHC has relied on an understanding of quantum field theory. So in a sense, LHC is also proving that the quantum field theory is the correct framework to discuss the interactions of elementary particles. In particular, there have been these heroic calculations of QCD that are crucial for the interpretation of the data. So we can see in this plot all the cross sections that have been measured and all the points on the data and how it agrees with the standard model. This, but behind these plots, there are, I mean, thousands of pages of work of the theory to calculate the Feynman diagrams and to evaluate the signals and backgrounds, etc., etc. But something that has made possible that work is something that has brought some connection with more fundamental aspects of QCD, of a field theory, for like amplitudes, KLT, and double copy, black holes, and an interesting aspect that I'm working on in these days is the idea that it's possible to discuss quantum field theories from a constructible point of view, namely just from the amplitudes trying to derive the structure of the theory. And this, for instance, this new method that have been developed recently have helped to have under control some of the calculations. For instance, like the 2 gluons to 2 gluons involves 4 diagrams, to 3 gluons 25, to 4 gluons 220 diagrams. Doing this by hand is impossible, and even with some computer help, it's very difficult. So people has discussed new methods that have been made possible to work these backgrounds and signals, like the Parquet-Taylor formula for the maximal helicity violation amplitudes, which are expressed in very close forms that they involve the spinor products, which will require a whole course and not only a seminar. And one important outcome of this type of work is that the calculations involving graviton scattering has been found that thanks to these so-called KLT relations have been calculated. And for instance, the amplitude at 3 level involving 4 gravitons, it has been found that it can be written as a product of 2 amplitudes involving gluons. So, and this is also for 5 and 6 particles. So this gives us this expression that general relativity is the Yang-Mills square. And this, in the heart of these KLT relations at the origin, was a connection with the string theory, which at least has been very useful in order to derive further properties of in quantum field theory.
Lorenzo, one more minute.
Yes, I jump to my conclusions. So we have the standard model, and we want to find an extension that will solve some of the problems that we have. And as theorists, as if we look at what Weinberg did, well, we are doing essentially the same. I mean, we are building one model after the other, trying to explain one aspect or other aspect. And the progress to choose to know which of those models is the correct one is from experiment. So we need to keep working on the colliders that we have and the other facilities, and think also about some future colliders that will help us to find which of the extension of the standard model is the correct one. So thank you very much for your attention.
No, thank you, Lorenzo. It was a very nice talk. It was a very good overview of the different areas. Okay, there should be some questions.
I don't see any raised hands. There's a couple of questions that were written in the chat. Javier, do you want to? Okay.
Javier Orduz, you can make your question, please. I think you are muted.
Yeah. Okay. Oh, his microphone doesn't work. So he said, what could the parameter be that tell us what is the next scale to new physics?
At this point, what we are kind of confident is that there is a new scale associated with the Planck scale. I mean, that's the for sure next scale. All other extension of the standard model, we are motivated by, actually we kind of fix the scale so that something is seen at the collider. But as far as I know, it's not possible to claim that there was one scale. For instance, for the discovery of the Higgs, there was a kind of no lose theorem that either one finds a Higgs particle or new interactions in W scattering. So in that sense, that was something for sure that was to be found at the LHC. But for new physics, we don't have an argument that will tell us that exactly this, there will be a new case. Just look at the neutrinos. Some models based on grand unification will say that the new scale for right-handed neutrinos, for instance, could be close to the grand unification scale. But these days, there are many models that are looking at right-handed neutrinos with the order of the electroweak scale, or even very light ones of the order of GeV. But it's the experiment that will give us the scale.
Mm-hmm. Any other questions, anybody?
No, from YouTube. Let's see if we are still, somebody's raising hand.
Well, okay. So then I think we can conclude the talk and the last session. Thank you very much to all the speakers.
Thank you.
So Salvador, you take over now.
Yes, so I just have some announcements before Edward officially closes the meeting. So I would like again to talk about poster sessions. We ask the participants who won the poster session to connect. So I will share briefly the announcement. So we thank the jury, as we said before, and for the poster sessions, we have Osvaldo Miguel Colín presenting CMS RPC longevity studies, and Andrés Ramírez Morales presenting frontiers in particle physics through precision experiments and machine learning. So we like to say that we have a very, very good poster sessions, which were actually mini talks. And it's the first time we try this, and we really thank everybody that did participate for this session. So I think Edward would like to give a public announcement before we go to the General Assembly.
Hi. Well, first, in the General Assembly, we will have some work from Alejandro Ayala that this year is receiving the medal from the Division of Particles and Fields, our division, He has been a very active member of the community. I think everyone that is part of the community knows him very well. He also is a former president of the Division of Particles and Fields as well. And well, I think he's more than deserved the medal that he will be receiving. In the General Assembly, we will discuss another things, but we will ask him to give some words about what the means of this and all the efforts that he has been doing for many years already, trying to build this international collaboration, NICA. Also, well, I would like to thank everyone. I mean, this was a quite complicated idea of organize this annual meeting in online form, but I think it works pretty much well, being the first time. We have very nice talk, I think. We have good interactions, and the poster session, which was at the end something like kind of has Salvador mentioned, mini presentations, mini talks, was really nice. There were some very professional videos presenting what they did. So probably it's a very good idea that because that is something that stays there. I mean, it's something that we can review later and we can actually share in addition to this. Also, this presentation were also on YouTube, and we were recording that as well. So for some time, we will have also the videos on YouTube if somebody that didn't have the opportunity to attend one of the presentation have the opportunity to go and check and constrain the presentation they want. So I really want to thank everyone that is attending, also the speakers that the exercise of trying this. We have international speakers that with different time zones, they try to accommodate and help us in the organization. Also, I would like to thank, well, there are some students, I understand, the Salvador, you have the names of the students that are still helping us. Salvador? Well,
sorry, I was mute. We have some people collaborating from that will be participating on the National Congress. They want to do a similar approach also for the posters. Their names are Victor Maya and Jesus Avalos, who were working, co-hosting and helping with the support technical issues.
Yeah, there is quite a lot of work behind, things of this regarding checking not only questions, but how it's going on YouTube, and if there are questions there. Also, if any problem that were solved at the end, the last minute. We have also, of course, the organization committee, Ivan, Pablo, that were helping us a lot in organizing this. So for everyone involved in this quite good effort that we tried with this difficult situation of this year for us, I would really like to thank everyone. And just to tell you, what you are seeing there is something that we will discuss. This is going to be in, well, probably we'll get some 5 minutes break, and then we, for the member of the Division of Particles and Field, we will have this General Assembly, and this is something that we are going to discuss the order of the day that we are going to present there, and in particular, something that is very important is the election of the next vice president. So thank you very much to everyone. I hope you really enjoyed, and let's see that if next year we will have the opportunity to meet again in person and continue with the important activity of our division. Thank you very much.